try it again. So, Violent Earth Lecture 2, Take 2. Looks like it's the right lecture this time. After the introductory videos that were pretty long and pretty detailed, these lecture videos should remain about 50 minutes, 60 minutes. So I'll try to go pretty fast and try to go not into excruciating detail on all these topics, but just in the nature of this class to remain as a survey to all of this information. Really, the goal here is for overall exposure to content and interesting things with supporting details, and then the supplementary information that's included on the online folders if you're registered for the class allow you a little bit more meat to dig into. Okay? This is our roadmap for today. Lecture 2 is the materials of our layered Earth, and this is meant to be, again, a survey of this basic material that you might find in a normal geology class that you would spend a whole 10 or 16 weeks looking at some of these topics. But today I just want to introduce, for use later on in Violent Earth, introduce the topic and a little bit of supporting scientific details of a layered Earth. Then we'll focus a little bit on chemistry and mineralogy, so going from the sort of Earth scale here down to the more atomic and mineralogic scale, and then using that to then transfer into discussion on rocks and a survey of all the basic rock types that we're going to be focusing on, or maybe not focusing on, but discussing here in Violent Earth. Okay? So this is not meant to be comprehensive. It's just an introduction to these things. You shouldn't come away as a mineralogic whiz, and you also shouldn't come away thinking, like, geez, am I supposed to know all of these minerals and all of these rocks? Again, this is really exposure. It's here to kind of lay the foundations of some of the material that we'll be addressing later in the rest of the 10 weeks of the course. Okay, so let's start off here with a nice image from phys.org of this concept of a layered Earth. And notice, I really like this picture because it doesn't have these nice distinct boundaries, but you really do see that there's a gradational change in some cases to the interior of the Earth. And this picture specifically is meant to illuminate the idea of a core, the core of the Earth. Okay, to back up a little bit, this image is a round Earth, right? A round Earth, that's not a new idea in the last couple of centuries. This wasn't a Columbus-founded idea, popular to contrary myth, particularly in the United States, that when Columbus found the new land, all of a sudden it was discovered that the Earth was round. Well, actually, Greeks, and here is shown Eratosthenes with his gigantic dome. Look at that Earth-sized head there. So no wonder he was able to find observations on the Earth to support that the Earth is round, and then to calculate a circumference, which of course to do circumference you need the calculations of radius to get to that. So even at that time, this is around 240 BCE, before the Common Era, Eratosthenes had correctly proposed that the Earth was around 6,300 or 6,700 kilometers to the interior. And so within an order of magnitude of this, which is pretty darn neat. Okay, now come quite a ways forward in time now to the 1890s, after the Common Era. Just based on sort of physical principles of observations on the solid Earth, so looking at rocks and being able to map those rocks and the distribution of those rocks, and then more so to calculate the densities of these rocks. So a density is the mass over the volume, or how much mass there is over how much space that mass occupies. And that density, if you look at average rocks on the surface of the Earth, like any of these things that are sitting out here in front of me, generally around 2.5 to 2.7, maybe 3 grams per centimeters cubed. So the important thing there is about 2.5 to 3 are normal rocks that you would go out and pick up and maybe do this exercise in the lab. Now, in the 1890s, there was enough known about all that when folks started to calculate the density of the whole Earth, which is, of course, you can't do that same thing in a lab. This was early surveyors that were noticing while they were surveying near massive mountains in the distance, the plumb bob, or the piece of lead that was meant to show a vertical line from their survey instrument. The massive mountain exerted a gravitational force, the mass there, on their plumb bob, and it would change the angle just a little bit. So using some of those, trying to back out some of those details to make an accurate survey, they were able then to make estimates of the density of the whole Earth, which turns out was like 5 or 5.5 grams per centimeters cubed, was much more dense than any of these average rocks you might pick up on the Earth's surface. So why the discrepancy? In the 1890s, the discrepancies there started to form a hypothesis that discrepancy arose because the Earth had a dense core to it. And that's what's shown here in this much later computer-generated image, that there is a dense core in the interior. And of course, this is something that today in our day and age we hear when we're at kindergarten or 3rd grade or 5th grade or science. Somewhere along the line, you have heard not just this is a hypothesis, but it's been proposed to you that this is fact, that this is data, and we have that. And I'm going to go through a little bit of how this has become known, or what tools we have used to understand this. So yes, in fact, there is a crust to the Earth, the really light portion of the Earth, the lighter silica-based rocks, the mantle of the Earth, which is composed of slightly more dense magnesium and iron-rich silicates, and then the iron and nickel metallic core of the interior. Iron has a density of about 13 grams per centimeters cubed, so it's very dense. And if you you figure the balance between those 2.5 to 3 grams per centimeters rocks out here on the crust, and the 13 grams per centimeters cubed of an iron core, then even given that, you can kind of estimate a size that would be needed of the iron core to make that average 5.5 grams per centimeters cubed of the whole Earth. So just interesting stuff. So they're great ideas. It's good on paper and in doing the mathematics of all of it. But how do we go about testing this? And that's what I want to expose folks to today, is the actual tests that are behind this. It's great to have this stuff proposed to us as fact, and they're not proposals in science. This is a rigorous testing methodology where these hypotheses first are ideas, and then they must be tested over and over and over in the scientific method. A really good example of this, I like Einstein's quote suggesting that 1,000 tests could not prove him right, or millions of tests could not prove his ideas right, but one test can prove something wrong. So that's the strength of the scientific method here, is that we're testing, and arriving at probable conclusions based on all that data and all those tests, or all those data. And it only takes one test with good methods that show something completely different to throw it all back into question, right? And for us to say, okay, we need to look at this in a different way. Okay, that's a little bit about the scientific method, but let's go back here to, again, find out how we can go from knowing this, or at least within those probable conclusions like we do today, that we have a layered Earth, and those ideas, those hypotheses proposed back in the 1890s. And fundamentally in between, we've employed this study, the study of seismology. Ology for study, size or seismo for earthquake waves. An earthquake is generated from a fault plane that's undergoing some sort of slip. So this is the fault plane. The rocks on either side of this, the hanging wall and footwall portions here, after enough stress is built up because of the tectonic stress that's exerted on this fault, maybe in this case in this direction, and these are being pushed and pushed and pushed, and then they strain, and that strain is the frictional release, the kinetic energy release of all of that built up stress, and that propagates through the rocks as vibrations, and that's shown here in a really nice animation. Well, it's not animated, but a really nice figure that's showing this, this vibration emanating outwards. And it's that vibration, it's moving in the form of a wave, and that's what is felt during an earthquake, of the up and down movement, or the side-to-side movement. We'll look at the different types of waves in just a second. Now, from these earthquake waves, there has been these instruments long ago, well, maybe not all that long ago for the instruments we use today, but these do find roots in China. There are some early devices were used with marbles coming out of a lion's mouth to be able to detect the direction of shaking. So they weren't detecting the severity of shaking and some of the things we can detect now with a seismometer, but those were early seismometers to detect earthquakes. Now today we use 3-component seismometers, 3 components because they have 3 components. One to test the up and down, right? Another to test the north to south movement, another to test the east to west. So with those 3 components, you can get a 3-dimensional vector of each of these earthquakes. So the 3-dimensional vector would be then pointing back to the origin source. So if you have one seismometer here, another one here, and another one here, then you can accurately locate the epicenter of that that earthquake. So seismometer here, here's again the radiation of those vibrations, those earthquake waves, and this little pendulum here, this little weight is hung here and is on this spring is allowed to bounce up and down, and then to draw this very characteristic squiggly line that we all know of, the seismographs here. They're sort of synonymous with earthquake movement. Any cool movie that you see that has earthquake movement, they usually show the little wiggly, squiggly marks. Now, this is all taken digitally today, right? We have the modern digital conveniences, and these are just ones and zeros that are showing us this type of movement. So these are recorded in data loggers in these 3 different components, and this is just an example, kind of a dummy example that's shown here that shows the different types of waves that we're using in seismology to really to do a whole lot of mathematics with to back a lot of this interesting information out. So here is a P wave or a primary wave, sometimes referred to as a pressure wave because they are compressional, kind of like a slinky where it slinks back and forth like this. Then the S wave or the secondary wave, notice it comes in second, also referred to as the shear wave because these are shear movements, like you would expect waves moving over the surface of a pond, okay, just as an example. And then much later, a later arrival time, notice this is in minutes here, the primary arrives first, the secondary arrives second, and then lastly, the surface waves, which are clearly, you can see the amplitude here, are much more severe. And it's those surface waves that actually cause most of the damage in an earthquake as well. So it's these things that are felt very early on, and included within them is some of the best data that we can use in comparing these arrival times of these types of waves. Okay, so we're using the study of these earthquake waves, which are recorded by this type of meter, like a thermometer is recording temperature, a seismometer is recording the earthquake waves here. And how is it recording those, or what does that look like? It's in these sort of graphs of squiggly lines, and from those squiggly lines is all of the information that is written on or carried on those waves. And that information is this vibrational information of the velocity of those earthquake waves, okay? Now, I'm no seismologist by background, okay? But I did have a chance very early in my geology career to install a whole bunch of seismometers around, mostly around Eastern Oregon. While it was my first geology job at University of Oregon, and those were being installed for a seismologist or a tectonicist at University of Oregon, Dr. Gene Humphreys, to learn a little bit about the interior of the Earth. So this method that I'm talking about here isn't just a method that was derived in the 1930s, which is when seismology started to be employed to look at the interior of the Earth, but it's still something that we use today to discover more of these details about the interior of the Earth. Okay, more on that later. But then later in my geology career, during graduate school, actually, so not much later, I was actually able to work for the Pacific Northwest Seismic Network, also out of University of Oregon. And really my job was to look at these seismographs from all the seismometers, permanent seismometers in this case, instead of these temporary ones, around Oregon, just simply to make sure that they were functioning. That was really my job. I worked for one of the technicians, or underneath one of the technicians, that would, if we found something that wasn't working, or most of the things he knew of, we would go out and do the repairs on those things. So I have never myself done any of this seismology or some of this complex mathematics that goes along with these, but I have been exposed to this. I've been exposed to the raw data collection, the seismometers, the seismographs, and getting to look at these things. So I have this globe picture up here from Google Earth. I use this to show the area of Japan, and then here's the Pacific Northwest. So while I was part of the Pacific Northwest Seismic Network, the 2012 large earthquake in Japan with the ensuing tsunami, that, really it's getting a little ways further back in our mind, but that should be recalled by most people as extremely devastating. The tsunami particularly was very devastating, and that was the Fukushima nuclear meltdown that occurred was caused by that, and hundreds of thousands of casualties and infrastructural damage. Now, the reason I bring that up, again, I was working for the PNSN during that time, and when I woke up that morning and I learned of that earthquake from some media source or news source, I went directly to the seismometers that I was supposed to be monitoring to see if that was picked up by those seismometers. Okay, so I'm way over here looking at these squiggly lines from here. Now, the National Oceanographic and Atmospheric Service, NOAA, has a map, a really nice detailed map of the tsunami that propagated across the Pacific Basin. And it took about 12 hours for the tsunami to propagate across here. And then in Crescent City, California, Northern California, there was a small tsunami, 30-centimeter tsunami, which caused some devastation in the harbor there. But that took about 12 hours to propagate across the ocean as an ocean wave. So that wave in the ocean moved at 12 hours, took 12 hours. However, the seismometers, the seismographs that I was looking at, the signal of that earthquake showed up within 9 minutes to these stations over here in the Pacific Northwest. So earthquake waves are traveling through the solid earth, and they're traveling quite rapidly. Okay? Just some fun examples that are there. Okay, now a little bit more details on the types of waves. Again, here's that slinky-looking wave, the P wave, and notice that as it's slinking along, it is in a pressure movement. Notice the box here gets first compressed and then elongated as the wave passes through. These types of waves move through all types of media. The sound that's coming out of my mouth right now is actually propagating as a pressure wave to our eardrums, or if you're live here in the classroom, to your eardrums, or it's being picked up by the instrument that's over here, by the computer that's then digitized. And then the shear waves, however, this is how we might normally think of waves on the ocean, that they're these large rolling waves like this. However, waves actually move as pressure waves in the body of water, but it's that pressure that allows the water to move up and then to move down. So waves in water are actually pressure waves that are moving across the ocean, though visibly on the interface between the air and the water, we visually see them as these shear waves, but the water is not moving in this sort of fashion. I bring that up because S waves can't move through water. S waves are able to move through solid media, but they can't move through air and they can't move through water. Instead, in those two, in air and water and liquids and gases or fluids, the particles, because they are not bonded together, but they are individually able to sort of have their own trajectories and velocities, those S wave movements are converted into P wave movements. So that's very important to understand that that's a property of these waves, that S waves cannot move through liquids, or well, they cannot move through fluids. That includes gases and liquids. But P waves can. They can move through solids and they can move through liquids. Okay, so let's talk about a few other properties of waves then, because this is really where the detailed portion comes in. Waves themselves their velocity is dependent upon the material in which they're moving through. Okay, so what does that mean? A minute ago, I gave the example of the tsunami moving through water, and that took forever to go, well, half a day to move through the Pacific Basin. However, the vibrations that are moving through the solid rock took minutes to go the same distance. That's a property of the materials through which they're moving, liquids and solids, but the way that that's manifested is a faster velocity in the solids. Okay, so what am I saying here? I'm saying that waves move faster through more dense materials, just like the waves that moved in minutes across from Japan to the Pacific Northwest in the rock. But it took 12 hours to move through a less dense material, or water in this case, or air. Air waves would move even slower in air. So that's one property of waves, is that their velocity is dependent upon the substance in which they are propagating through. Okay, so velocity of seismic waves depend on the material properties of the rock through which they move. Okay, now we're going to focus on just rock rather than the other analogies. If you have a lower density rock, say 2.5 grams per centimeters cubed, and a higher density rock, 2.7 grams per centimeters cubed, the waves propagating through them will move slower through the less dense stuff and faster through the more dense stuff. Okay? Now, why is this important? If you have the hypothesis, the idea that the Earth has a more dense portion in the center, or in the core, or in any portion of it, we may be able to test that with the velocity of waves, right? And to test this without drilling down to it, we can't do that. We can only drill maybe the most 12 kilometers into the Earth. You can't dig an open pit mine. You can't take a vehicle made of unobtainium, like in some sci-fi movies that are out there. So we have no way to physically do this ourselves to see what's down there. So we have to use remote sensing. We have to be able to do this remotely from afar. And we have to use sensors like seismometers to pick up on these small vibrations. So using remote sensing and the properties of waves, it was conceivable to folks with this hypothesis that we could use the properties of waves, if we can detect the waves, to then understand something about the interior of the Earth. Okay, now how does this help us? How do waves help us, right? If you're on one side of the Earth and the vibrations are propagating through, and you pick up the vibration on the other side of the Earth, if that wave is traveling through less dense material or more dense material, that changes the velocity. So if we can come up with a model or several models of the interior of the Earth, and then after, say, a year of collecting all of this data from seismometers around and comparing those arrival times, you can start to map out the regions of the Earth where it is less dense, or the regions where it is more dense, right? If the waves are going deeper and the Earth is getting more and more dense in the interior, then they're moving faster and faster and faster until they hit a more dense area and they move really fast. Okay? So all of this stuff is helping us to remotely sense the composition, or at least the velocities of waves in the interior, which is telling us something about the composition. Maybe not the chemistry, but about the density themselves, which is related to chemistry. Okay, so also, not only do waves move faster through more dense material or slower through less dense material, but also heat, temperature, changes the density of materials, right? If you heat up some water, that water, all that heat is vibrating the molecules more, so they take up more space, right? So 100 milliliters of hot water takes up, well, sorry, I shouldn't say millimeters, 100 grams of hot water takes up more space than 100 grams of cold, dense water. It's just the heat that's contained in there. Those molecules are vibrating around, and they're repelling or bouncing into one another and creating a little bit more repulsion. So, because density is also related to temperature, we can also back out some of those properties of the rock. Waves are going to travel more slowly through hotter material, because hotter material is inherently less dense, because it has more vibrations to it, so it's a little bit less dense. Okay, so hopefully all of these properties make some intuitive sense, and then it's from this really intuitive sense that we can fine-tune those details and do a whole lot of mathematics that I don't really understand. I've never done any of this stuff, right? But it is knowing that people can do this stuff and then understanding these fundamental principles and the properties that make logical sense, right? Okay, so moving on, again, if we can conceptualize a couple of different models for the interior of the Earth. So why models, right? Again, you want to have the hypothesis that there is a core. Okay, that's one hypothesis. Well, you need to have alternatives. So when you're reading all of the data together, that if it doesn't look like what your hypothesis is, you don't make it fit to that hypothesis. No, you go, well, maybe it's something else. If you've never thought of the something else, it's really hard to conceive of that when the data is showing you something else. If you're ironed to one thing, then you're going to find that one thing. That's why it's really important as scientists that we have multiple working hypotheses. It's not just the one thing in your one idea, no matter how much you hope that it is. Actually, what's much more interesting and fun is when it's not something that you hoped it was, right? Or not the thing that makes intuitive sense right away, but revealing something else by looking very deeply at all the data together. So multiple working hypotheses. This is just one model that I'm showing here, and this is conveniently the model that the data support. But you could also have similar competing models as they did in the early 1900s, which what if we have a unifying density in the interior of the Earth and no layers? Then these earthquake waves, as they're traveling, maybe would not hit a boundary layer at this portion. Okay? So a boundary layer, notice that what's happening here is a different property of waves. This is called reflection or refraction. So there's two things that happen to any type of waves, light waves, sound waves, vibrational waves, if you go from one density of media into a higher or lower density of media. So for instance, let's say air into water. Like if you're sitting by a pond at night and you shine a flashlight into that pond at some sort of angle, that ray of light will propagate into the water, that's fine, but it'll slightly change angle. So where you're pointing in isn't exactly where the light beam is going to go, right? Hopefully you've experienced this, or another way to experience that really quickly is in a glass of water, putting a straw in the glass of water, and you can see the straw is slightly offset. That's an optical property of the difference in density between the air and the water. Another thing that happens to that light beam is it gets reflected like a mirror surface. So similarly, because light is a wave, similarly, waves, vibrational waves moving through the Earth will reflect or refract when they hit boundary differences. So this boundary going from this lighter silicate material of the mantle to the much more dense iron and nickel core of the interior, that's a boundary difference going from lower density to higher density. So there is refraction and reflection that occurs there. Now, in the model of a unifying dense Earth, there's no boundary layers then, right? So that was not noticed. It was noticed that a seismometer here would not just pick up the signal of that earthquake moving across across the upper portion of the mantle, but it would also get a much later signal of that same earthquake as the waves have propagated down and then been reflected from the core mantle boundary back up. So a much later arrival time to show up that shouldn't show up, right? That really shouldn't show up if the earthquake waves were able to propagate all the way through. It shouldn't be reflected back unless there's a boundary layer. Okay? So coming up with multiple models, folks or early seismologists were able to compare the collected data from seismometers, do a lot of math and compare all this together and to send it to their buddies, and they would do all of this math, and they would repeat all of these tests, and slowly, over time, none of this stuff, science just doesn't magically happen overnight, right? This takes teams and hundreds of people looking at this stuff and unveiling this slowly through time. It became apparent that we have a layered Earth. Not just a layered Earth, but also that the hypothesis of a dense iron core in the interior was correct. Okay, so hypothesis, tests using seismology, and the conclusions based on all of that data, or the probable conclusions based on all those data, say we have a layered Earth. Okay? Now, this model is pretty interesting. Now, I want to underline a few portions of what's written here. This is the wave arrival times based on our model. That's actually its own detailed science or study of seismology, and that process is called tomography. Okay, graphing out and these different model differences and using the using all of the data that rides on those seismograph waves, and then interpreting those and comparing those is tomography, or coming up with conclusions. Seismology is really the look at those waves specifically and trying to find out where the earthquake originated. Now, this T, it's really important to point this out, and then to look at the date right here, Harold Jeffreys in 1926, this was originated in the earth sciences, this T word, this tomography word, to do this. But it didn't take long for a different set of sciences to say, hey, I bet we can use waves to figure out all sorts of things about the interior of stuff that we can't get to, or maybe that we don't want to get to anymore. So with the Earth, we just can't get to it. Fundamentally just can't, right? But we can't cut the Earth open and do this, but we could conceive of models. However, things like the human brain, we had cut open human brains routinely before and learned about them, early medical students, right, on cadavers. So we have really good models of what the human brain should look like. But what if you don't want to cut open a healthy brain to do exploratory surgery to see if there's a tumor there, or to see what's going on in somebody's brain? What if you could use waves passing through the flesh or the brain of somebody, and then using the model of a normal, healthy brain as comparison, you could find asymmetries or higher or lower velocities within that, say, within that brain to find if there's any sort of unhealthy tumor growth or something. And so I think that you're picking up on what I'm laying down here, that the T here is the T that you would find in a CT scan. The same thing that we would do in the medical sciences to find tumors in the brain. This is the same thing that the medical sciences do, the same same technique that is used in the medical sciences. So this is something, this doesn't live in just the abstract world of stuff that I'm telling you, seismology, tomography, that this has real applications besides just learning about the interior of the Earth and layers. That this is something that we use to understand our own bodies and to understand when we have something unhealthy going on in our bodies, okay? It's not the same technique, but things like X-rays also are based on waves, right? The movement of waves to be able to tell something about the interior of the body, which we don't want to cut open just to explore it, okay? Remote sensing is very powerful. All right, after all of that, here we are 30 minutes later. The layers of the Earth, the core, the mantle, the crust, it's really easy to conceive of those, and we've talked about those earlier, and you've heard about those since you were in kindergarten, probably. Just like an egg, they say, right, with the shell, and then the egg white, and the egg yolk. Okay? Now, let's go a little bit deeper, and I want to do this because this becomes really important later in this class in Violent Earth or in any geological sciences. The Earth, it's not that it's just more complex than that. Yeah, it is more complex than that. It's more complex than I can really understand. But by focusing a little bit more on these details, we can also back out some more understanding. Right? So I want to then talk about the mechanical layers of the Earth as different from the compositional layers. So the compositional layers, we still have a core compositionally, but that can be split into two different mechanical layers. An inner core, which is a solid metal sphere of iron and nickel, and then the liquid outer portion that's still hot enough and not under immense pressure, quite immense pressure, to still be a liquid. Now, slowly over time, that inner core is freezing and is absorbing, well, not absorbing, but as the outer core liquid portion freezes and turns solid, the inner core of the Earth is growing through time. And it is the difference between these two and the liquid outer core, that liquid metallic core, and iron inner or solid iron inner core, they give rise to our magnetosphere of the Earth, right? So anytime you've used a compass to tell north, anytime that we use magnetics for anything, like say just as simple as a USB drive or a magnetic stripe on a credit card or something like this, magnetics and magnetic properties arise from the interior of the Earth like this. And of course, the gigantic sphere around the Earth, the magnetosphere that protects us from harmful solar radiation, is also very important to biological life here on Earth. And that all arises from the interior of the Earth. So it's not just a core. There's an inner and outer core that are moving and spinning at different rates than the rest of the Earth. Okay, very important. Then also we can break up the mantle into a few different boundary layers. Now I want to first look at the lithosphere because I said this is all the mantle. So what happened to the crust? Well, the lithosphere also includes the crust. The crust is like minuscule. It's these really rigid rocks on the outside that are touching the cold vacuum of space. It's cold out here, right? It's cold in the atmosphere, and it's hotter the further you go into the interior of the Earth. So that gives rocks a property of behaving kind of, we call it plastically, right? Or ductily, where they're able to flow through time. So when you apply stress to them, just like a piece of chocolate, as my early instructor would point out, right? As you apply stress to cold chocolate, it's brittle and it'll break. But if you warm that chocolate up a little bit, and then you try to break it, then it'll kind of ductively, plastically form and flow. So think of the Earth very similarly. The crust is rigid. The continental crust of the Earth, about thin crust 10 to thick crust about 40, 50, 55 kilometers, or the oceanic crust, which is all about 10 kilometers thick. That's really little compared to the 6,700 kilometers of the rest of the Earth, right? Now, the rest of the outer portion, the rest of the lithosphere, is the same composition as the mantle. So compositionally, we have the lithosphere, which is made up of the same material as the mantle, but it's also relatively rigid when compared to the lower layer, which is the asthenosphere, this next layer, the asthenosphere, which is much more plastically behaving. It is the lithosphere that make up the plates of plate tectonics that are much more brittle, and they're allowed to crack and to move independently of one another, right? Now, the asthenosphere underneath is kind of like the dough or the putty on which these porcelain plates are writing, okay, that allow them to move independently underneath of this kind of more squishy, silly putty-like layer. Okay? Those are just analogies, by the way, when I say silly puttery or dough or something like this. The rheology of the asthenosphere it's something that escapes me, right? I think we can kind of comprehend it through analogies, maybe. It's the best way that I do it. But I would not argue that I understand very well the rheology or the properties of the asthenosphere in that way. Other than it is very different and less rigid than the lithosphere above it. The asthenosphere is also a very special layer of the Earth. This is the portion where there's partial melt, it's all solid, right? Everything we've talked about, except for the outer core here, is solid material. The rest of the mantle, it's all solid. However, in the asthenosphere, the seismic velocities show a major decrease here in the asthenosphere. Now, it's not molten, but it may have partial melt. That's actually where all of Earth's melt first derives, is from the asthenosphere. These are processes we'll talk about later in the course. Flux melting and decompression melting, both of those things first originate, the melt that comes to the surface of the Earth originates in the asthenosphere. So it's this odd layer that kind of rides the balance between the overlying pressure and the immense heat that's propagating from the interior, the primordial heat and radiogenic heat. And it's kind of this balanced zone that is not under so much pressure that it remains solid, and it's not so hot that it's liquid or molten. Okay, more on that later. And then the mesosphere here, that's just the rest of the mantle, all the way from the asthenosphere here, where seismic velocities begin to increase, all the way down to the core mantle boundary. Okay? And there's some really interesting things that happen in the mesosphere, and all of this stuff is probably not as simple as vertical layering. There's probably a lot of horizontal heterogenies that occur, and that is now the interest of seismologists and tomographers today. Yes, we know we have a layered Earth. We've known this for quite some time, and the mechanical layers are also known. But how about we look at these other small, minute differences in the mantle itself? This is also telling us about some really interesting things. So here is a depth slice of about 150 kilometers. So just like the layers of an onion, if we were to peel those down, you go from the first layer, second layer, third layer, fourth layer, or 25, 50, 75 kilometers. This is a slice at deep, about 150 kilometers within the Earth. And this is looking at the seismic velocities within that depth profile. And here in blue is colored the seismic velocities that are fast. So what does that mean? That means that it's dense, and that means that it's either dense and cold, or well, it's dense and cold, right? Comparatively to seismic velocities that are moving slow, which is associated with being warm and less dense. Okay? So here we have the west coast of North America is mostly these lower seismic velocities, warm, and the east coast mostly these faster seismic velocities. But look at these really interesting heterogenies that occur. That's interesting to the Earth scientists, right, or to the scientists. Anywhere where you find things that are different than the surrounding area, there's something interesting going on there. So by doing this with tomography, we're now able to focus on some of these interesting heterogenies here and then ask those questions. What's going on, right? What can we tell from the surface or from looking around at different depth slices to figure out what is going on here? I'm not going to illuminate any of that here today, even though it's very interesting. Just want to point it out. Another method that's used is looking at the mantle itself and the asthenosphere specifically, I think, and using the property of anisotropy. So we'll talk about mineralogy in just a second, but the mantle of the Earth is mostly made of the composition of the mineral olivine. Now, there are some transitions that happen to that mineral as we go, but we'll just kind of blanketly call it all olivine. Olivine has, just like all crystals, they have three different axes. Here's just a piece of kyanite to use as an example. We have the long axis, or the C-axis, and then there's an A-axis and a B-axis, right? Just like the three components, north, south, east, west, and up and down that we talked about with seismology. Now, waves, again, their velocities depend on the properties of the material. It turns out that waves are able to travel slightly faster along the C-axis of an olivine crystal than they are across the A or across the B-axis. So that property of olivine allows folks doing anisotropy, which is this principle, to look at the arrangement of the minerals of olivine within the mantle. And the arrangement then is telling you something about the flow. If the asthenosphere is flowing, then all of these olivine crystals would be oriented in the direction of that flow, right? Just like just like anything that's flowing, any of these particles may become aligned to that. And what's shown here is the direction of the c-axis of those olivine crystals in the asthenosphere, showing that we have some sort of asthenospheric flow around the globe. And this is also very interesting, right? This tells us something about what's going on in the mantle. Okay, so that's a really broad look at seismology and how we know about the interior view, our layered Earth. Okay. Here's a little recap of that, starting with Eratosthenes and the round Earth, the hypothesis of the dense core, seismology, which we went into a little bit more detail probably than I expected, and then today we continue to resolve some of those differences in the interior using tomography. Okay, let's do a little bit of chemistry then. So chemistry, here's a good example of the silica tetrahedra. This is the fundamental building block of all minerals. Well, not all minerals, but most minerals that make up the Earth's surface, somewhere around 98%, and then therefore rocks of the Earth. This is a silica atom that's here in the middle, and then around that are 4 oxygen atoms. Now, we'll come back to this. I just wanted to point out exactly what this is and why it is on the cover of the chemistry slide. Let's back up a little bit to some basic chemistry here. This isn't going to be a survey of chemistry class, but I just want to back up to something like the structure of the atom. So an atom is a generic term that describes this fundamental, indivisible portion of matter. It turns out it is actually divisible. It's just not very stable in its divided portions. But all matter is made up of these atoms. And it is the difference between the numbers of these smaller particles within the atoms that we call elements. So one element, like oxygen, would have a certain number of these things and a certain number of these things that's different from, say, a silica, which would have a different number of these things and a different number of these things. If you want to know about all those specific numbers, that's on the periodic table of elements. That's what that arrangement of that whole periodic table is it's showing us the numbers of these things, and these things within each one of those elements and what makes each element different from the next one. Okay? So what are those things that I keep pointing at, right? We have the electrons. Those are the negatively charged portion. Really, it's more proper to call these things probably an electron cloud than to point at them and say the electron is there. Again, further discussion on that in, say, a chemistry class. It's very interesting. But not really necessary for our needs here. Those are the negatively charged portion, and they also weigh virtually nothing, from my understanding. Their mass is negligible to the whole atom itself, right? You could lose a whole bunch of electrons, and the mass of the atom is not really going to change detectably, from my understanding. I'm sure that that's an oversimplification, and that there is, of course, some change that is occurring, even detectable to really sensitive instruments. So my point here is to point out that most of the mass, or all of the important mass of the atom lies in this thing, which is called the nucleus. And within that nucleus, what's shown here in the slide are these kind of golder and whiter colored particles. Some of those are called neutrons, and some of those are called protons. The protons are the positively charged counterparts to the electrons. So it's those two things, the positives and negatives, that are really giving rise to chemistry of the greater sense. So whether you have a deficiency of electrons, that would make you more positively charged, or a surplus of electrons, that would make you more negatively charged, so the atom more negatively charged. And then it's the reactions between those two negative or positively charged particles where we have chemical bonding and chemical reactions. Okay, I think it's also really important to point out, I didn't put this on the slide anywhere, that this is not to scale, NTS. Electrons are not this big compared to the protons, right? The nucleus is not this big compared to the whole atom. In fact, there are analogies that say things like the size of this building, which I know you're not here at this building, but the building is got a couple of floors and it's maybe about 100 meters, and in that direction, 75 meters in this direction. I don't know, it's a decent sized building. And for a building of that size, the nucleus of the atom is something like the size of a speck of dust, right? Or another way to say that is the nucleus is incredibly small compared to the size of the atom itself. So it's the electron cloud, or the electrons, that take up most of the space. But of course, the electrons aren't taking up the space. They're small, and they don't really have much of a mass. It's the space that they're supposed to occupy that takes up most of the atom, where the nucleus is very, very small, but also is the most dense portion of the whole thing, containing the particles that have mass. Okay? One more detail that will come up later in the course that I should bring up now while we're focusing on these. I already mentioned the difference between elements is the difference in the numbers of protons and electrons. Okay? Now, you change the number of protons, you're going to change the whole atom itself. But if you change the number of neutrons, the neutral particle that are here, you don't change the fundamental electrochemistry of the atom at all. You don't change how it reacts with another particle. But you do change its mass because you're taking away a big chunk of this thing. So you're fundamentally changing the mass, but not how it reacts with other stuff. We call those things isotopes. So for instance, oxygen has a couple of different isotopes, 16 and say 18. That means that it has, some oxygens have 18 neutrons, and some of them have 16 neutrons. Well, that makes a big difference when we're talking about the mass. And why would mass of an atom matter so much? If say, gravity is allowing a water particle to evaporate, to rise up into the atmosphere via the evaporation process, then that evaporation process, or going against gravity, is going to be a lot easier if it's a lighter particle. So oxygen 16 is able to rise or evaporate from the ocean much easier than oxygen 18. So that makes water that falls from the sky, we call that meteoric water, or snow, or rain, these kind of things, is much richer in oxygen 16 than the ocean, which is much more rich in oxygen 18, because all the 18 gets left behind as the 16 goes away. Now, I just bring that up because that's going to be important isotopic chemistry, or at least the awareness of isotopes, for some later conversations in Violent Earth, for supporting details. Again, this isn't meant to be comprehensive. This is really an exposure class, right? To expose one to all these different topics, sort of out of a respect for the Earth, an understanding of our friend, as we talked about in the last really long videos. But I want to give supporting details to all this stuff, and not just say, blah, 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 here it all is, right? But it's the details that are important, right? It's not all about the details, it's about the big picture and understanding this. But you can't come away with a great understanding unless you don't understand some of the details, or at least that there are details to be understood, okay? So as another instructor used to tell me, it's not about the details. Don't get bogged down in the details. But it's all about the details. Okay, kind of weird oxymoron there. Okay, moving on from the atoms, let's look at some of the important atoms that we'll talk about in the geosciences. Really right here, all on this one slide. Ions, then, are the charge of the element. So we call elements that have a positive charge, they're overly positive, which means they have a deficiency of electrons. Those are cations. Or those that have a surplus of electrons, or a more negatively charged, like say oxygen over here, they have too many electrons. Those would be called, or those are called anions. So here are all the anions, negatively charged ions in blue, and all the cations over here, positively charged ions in red. The positively charged cations are really the important things when we're talking about mineralogy, the differences between minerals. The main anion that we would use in the geosciences is oxygen. Okay, so silicates, if you go back to that silica tetrahedra in the opening chemistry slide, that is the silica cation with 4 of these oxygen anions. Okay, so oxygen is going to be our fundamental anion, and then exchanging these cations to neutralize the particle is what we will mostly use in the geosciences. Okay, now let's take a look at some of these things really quickly. I want to point out some of the charges are the same, and then some of the sizes are the same. This is not only interesting, but this is important for the shapes of minerals or the shapes of compounds as these things are bonded together, and the size or the relative charge of those things. So take iron. Iron has 2 different oxidation states, iron 3+ and iron 2+, and they're a little bit different sizes, right? So they're different charges and different sizes. However, magnesium is also a 2+, just like iron 2+, and look at its size. It shares a very similar angstrom size to iron. So iron and magnesium, because of their size, they can replace one another in a mineral or in mineral geochemistry. Now, that does throw off the charge balance between 2+ and 3+. So the crystal or the compound is going to have to adjust for that and deal with that by adding in more cations to that situation. Similarly, potassium, sodium, and calcium. Now, they're not exactly the same size, not quite as close as magnesium and iron, but they're relatively close. Calcium and sodium can replace one another. And at higher temperatures or higher vibration rates, if the atoms are going like this because they have all this heat, this vibrational energy, then when they're spread apart, a big jumbo potassium cation can fit right in there, right? So at higher temperatures, potassium can actually fit in replacement for sodium and calcium in some of these crystals. Similarly, aluminum and silicon, about the same size, different charge. So aluminum can replace some of the silica in those silica tetrahedrons. We call those aluminosilicates. Those are most of the feldspar group. Aluminum is a really common element on Earth, as we'll see in a second. All right, I just wanted to point out all of the major cations that we would be using in the geosciences and the anions. Okay, this is this nice little pie graph here is showing kind of the distribution of some of those cations and anions of the Earth's crust. This is important to point out that this is of the Earth's crust and not the whole Earth, so this doesn't include the mantle of the Earth, and this doesn't include the iron-nickel core. What I want to point out here is that half of the Earth's materials, atoms of the crust, are oxygen. Almost half of any given rock or any mineral that you pick up is oxygen anions. And those oxygen, just like the intro slide, the silica tetrahedra has 4 oxygen and 1 silica. Those oxygen are then bonded to either silica, like the silica tetrahedra, and or the rest of these materials. And it's all of this stuff together that makes up the diversity of mineralogy. And then therefore rocks. Any of the rocks that you pick up are made of multiple minerals, and each of those minerals contains a different ratio of mostly oxygen with silica and then some of these other things sprinkled in. And that's what gives rise to all of the great differences within the mineral families. Okay, this is just for general awareness here. We probably won't come back to anything like this, but I will continue to point out that most of the materials of the Earth's crust are oxygen by atoms, and then silicon with some of these other major elements: aluminum, iron, calcium, sodium, potassium, magnesium, and others, say sulfur, and well, what else would we have? Sulfur, uranium, things like this. Okay, all right, let's get back to chemistry. Again, chemistry is occurring between these particles. So what we were just looking at is subatomic chemistry or kind of subatomic physics, the details of what's contained in each of these atoms. But it's the reactions between the atoms that give rise to chemical reactions. So it's bonding between each of those anions and cations that give rise to compounds. So here in this example is the cation sodium. Again, this is something that is has a deficiency of electrons, so it's positively charged. And then over here is a chlorine atom that has a surplus of electrons, so it's negatively charged. Now, either of those two things, those individual atoms or elements, are not necessarily, will be anthropomorphic here, they're not necessarily happy in that situation, right? Everything, because of entropy, wants to kind of be neutralized or be relatively stable. And the way for these two particles to be electrically stable is to bond with one another. One has too many electrons, one has too few. So hey, how about we trade that electron? Now, trade it back and forth, and that's what's called an ionic bond. They can both be using that electron, getting rid of that electron, so it's neutral, with this one, but that bonds them together in some sort of electronegative state. Okay, so they are fundamentally attracted to one another by this relationship, but this ionic bond is also really easy to split up because, after all, it's just the attraction of a negatively charged particle that's holding them together. So as soon as another particle comes along that it could also trade an electron with, or even better, if it could be neutralized without trading the electron, giving something up, that's even better. And this is like a water molecule. Water is a polar molecule. It has a positive side and a negative side. So if a water molecule comes in here, and that positive side is able to give that electronegative energy to the chlorine atom, then it no longer needs the electron away from that sodium atom. So that will split those two things apart. That's why water is oftentimes called the universal solvent. Its polar nature can break up almost any ionic bonds because no longer do those two particles need to trade that electron back and forth. Okay, now let's look at a lot stronger bond here, and this is the covalent bond, where the atoms are sharing that electron. So here's a carbon atom, or 5 carbon atoms together, and those carbon atoms, they each have a deficiency of 4 electrons in their furthest outer region, their furthest outer shell. If they could only share each of their electrons, those 4, with the other one that doesn't have 4, then by sharing these all together, they are then covalently bonded. Okay, so by sharing or trading something, you're inevitably bonded together by that process. So these two are always bonded together, those particles. But the trading is a lot more weak, because you can always give the thing back, right? Is a lot more weak than actually sharing. I think that has interesting anthropomorphic implications. Okay, this is about as detailed in chemical bonds that we're going to get, but this is really important to understand that ionic bonds are weak and covalent bonds are strong. Why is that important? As we look at minerals themselves, there's a property of minerals that arises from the strengths of the bonds. Okay, here's that pie graph again, or similar pie graph, half of the Earth's crust being oxygen, and quite a bit more being silica, iron and magnesium and aluminum to follow. Now, that's the silica tetrahedra, just those two things. So when you think about rocks, I want you to think about rocks in these chemical terms now, okay, as mostly oxygen. Now, remember, this is not breathable oxygen. This is not respirable oxygen. The stuff that you're breathing in your lungs right now is O2. 2 of these oxygen molecules bonded together with one another. Okay, different stuff. We'll talk about respirable oxygen later in the course. The silica tetrahedra is what makes up all of the materials that you pick up. So start thinking about the Earth in this chemical lens, that it is these little silica tetrahedra bonded together in different shapes and different orders with a few other cations that are thrown in. It's really all it is. It's a simple chemistry of the exterior of the Earth. Now, okay, so I just said it's a simple chemistry. It is, in this fundamental way, but I want to show you slightly more complex when you add in the rest of those cations. Adding in those cations, remember, because they're different sizes and they're different charges, is going to change the shape of those crystals. And by different shapes, I mean if you have Legos, I like Legos, I play Legos with my son, right, who has a lot of Legos. If you have different sizes of Lego bricks, you're able to make different shapes. So for instance, if you have some big squares, like some 4x4s or something like this, and you try to make something with those, you're limited by using the 4x4s. But if you use the little 1x's, then you're able to make a different shape than you could with those larger particles. And this is kind of similar with mineralogy then. With different arrangements, different numbers of those silicate tetrahedra together, there are different arrangements to make up different minerals. So we have individual silicate tetrahedra or isolated tetrahedra like olivine, ring silicates, chain silicates, double chains, or chains that are together in a giant sheet, the micas, and then more of these complex frameworks, the feldspars and the quartz. Okay, the next slide, these images right here aren't particularly important other than associating an image along with those words I was just spelling out, the isolated or the ring. Now, those are not details I'm going to expect you to remember or say test anybody on. But again, it's the supporting details that give a lot more credence to this. I have a couple of examples of these minerals here, why they might be called sheets. This is a muscovite or a mica, type of mica, and it's a sheet silicate. Notice that it's very thin, like a sheet of paper in this dimension, right? And then much wider in this dimension. It's a sheet silicate. It's very easy to flake into sheets, okay? That is because the bonds, again, the ionic and covalent bonds here, the bonds between atoms in this plane are covalent. They're stronger bonds, where between the sheets, between these large sheets, the tetrahedras that would sit on top of this are weak bonds. So it's able to cleave or to break along that weakly bonded plane. And that is a property of minerals that we call cleavage. It's able to cleave along those weakly bonded areas. And cleavage is one of the properties of minerals that is really easy to tell. When we're trying to identify one mineral from another, that is oftentimes one of the easiest and most repeatable ways you can tell the difference between, say, an amphibole crystal or a pyroxene crystal or a quartz crystal, right? It's all in those observations. Okay, moving on from here, I want to look at all of the elements that we were just discussing and then matching those up with the minerals that I just listed. Now, this is something I'm going to ask you to remember. These mineral names are going to come up a lot, particularly a set of about 5 of them, and we will use these mineral names in Violent Earth. Now, the minerals are only important because they represent a chemistry, right? I'm going to show you the difference between a quartz chemically and a pyroxene or an olivine chemically. So it's not the names or the look of the crystal that I want you to know. It's that they represent 2 totally different chemistries of the Earth. Okay? And later in the course, of course, this will become really important. So some of the main elements that we just looked at, oxygen and silica, that makes up the silica tetrahedra. So if we have a rock that is purely silica and silica tetrahedra, that's what's referred to as a felsic material. Now, if we add in some of the heaviest materials, silica is really light, if we add in some of the heaviest materials, iron and magnesium, okay, we call that mafic. Iron and magnesium, Na for magnesium, Fic for ferrous or ferric iron. Okay, so the chemistry of the material is actually written in the name right here. The mafic materials are the heavier minerals, or the minerals that contain heavier elements. And then there are the alkaline groups of, or the alkali elements that make up the alkali minerals, okay, like calcium, sodium, and potassium. Remember, they're all about the same size in angstroms, so they can replace for one another oftentimes. So these make three natural groups that we're going to separate the minerals into, along with aluminum that's the same size and one off the oxidation state from silica. So that is also going to find weight in this grouping of minerals. Mineral is something that maybe we take for granted, the name there, mineral. These are not the minerals that you see on the back of the cereal box, right? An organic mineral that you may need for proper metabolism. But these minerals that we're talking about have a 5-part, very specific definition. It is a natural material that's created by a geologic process. We're also talking about solids here. We're not talking about liquids or gases or anything like this. It has a definable chemical composition. That means that we can write down some sort of definition to this thing. So it is not, we're putting brackets on what it could be, right? So it's either iron and magnesium silicate, or it is an aluminum calcium silicate. Okay, so its chemistry is definable, though it may have different amounts of those iron and magnesium within it. And then, as I already said, it must be crystalline. So you can have many of those things, but maybe not have them bonded together as a crystal. So say like a glass fits a lot of those properties. You can have natural glass, it is a solid, but it is not a crystalline material. Those silica tetrahedra are not bonded together in a crystalline way. Okay? So that's the 5-part mineral definition. And here are the 8 rock-forming minerals. These are the main 8 minerals that any geology student knows by heart and can tell the difference between any of these. But here in our class, these are really chemistries, and I want you to think about them in these couple of different chemical groups. The olivine, pyroxene, amphibole, and biotite are those that contain iron and magnesium. So we're going to call those mafic materials. Okay, then you have the muscovite, plagioclase, and orthoclase. These are what are oftentimes called feldspars, the plagioclase and orthoclase. And then muscovite as well. These 3 contain aluminum. So we're going to refer to those as the aluminosilicates just in this kind of introductory course. And then lastly, you have the mineral we call quartz. And quartz is a really common mineral. If there's one mineral crystal that you recognize, it's probably quartz that has this really nice quartz point, sometimes like a crystal when you're thinking of a crystal. Okay? And quartz here is pure silica. This is actually the same composition as glass, like basically automotive glass or beer bottle glass or something like this. That is mostly silica tetrahedra. But again, the difference is that all our quartz has a crystalline nature to it, where glass has no crystalline nature. It's not bonded together in a crystalline solid. So quartz is very common and it's pure silica. Okay, so these are the groups that we're going to break the minerals into. We have the mafics, the aluminosilicates. 2 of those are known as the feldspars. That word will come out quite a lot, feldspar this, feldspar that. And then the pure silica or the quartz material. Okay? That kind of ends the little primer on mineralogy and chemistry. And the real reason to go through that is minerals are the fundamental building blocks of rocks. And rocks are the fundamental building blocks of the earth. So if we're trying to understand our good friend here, what are you made of and how do you function and what is our relationship, it's really essential that we not only understand the rocks that it's made of, but the building blocks of minerals, and then minerals have their building blocks as atoms, right? Atoms and elements. Okay, and that's about the levels of scales we're going to go through. Okay, let's look at a few different rock types, and this again will just serve as a basic primer for the rest of these. Igneous rocks are those types of rocks that are made of crystals, like all rocks are, but these are crystals that formed in a melt. Okay, they solidified from molten material. So if you start with a magma batch, or you start with a lava, like a lava flow in Hawaii, that is creating an igneous rock when it freezes. Okay? This might be kind of funny to you to think of it that way, but as a magma or a lava freezes, that is making a rock, an igneous rock in this case. You might separate those two. A magma that forms in the interior of the earth is called an intrusive rock, and then a lava that flows on the surface of the earth is also different from that. It's called a volcanic rock. Okay, so those are two different groups that you might separate igneous rocks into. Now, here on this table points out how we name and classify igneous rocks. And we're not going to have a chance to go through all of this in detail in Violent Earth, but I just wanted to point out fundamentally, because silica and oxygen, as we saw in the chemistry portion, are so important here, that's how we name rocks, is based on their amount of silica dioxide. You have the ultramafic stuff, mafic, for ultra heavy in iron and magnesium silicate materials, like peridotite. That's what makes up most of the interior of the earth, with the exception of the core, most of the mantle, and that's the mineral olivine. Okay, then more or higher amounts of silica dioxide, from about 40% of the ultramafics up to 70%, is the natural variation in Earth's materials. If we go slightly more silica dioxide, made up of olivine, pyroxene, amphibole, and the calcium-rich plagioclase, we have basalt, that's the volcanic material, or if that material freezes in the interior of the earth, in a magma chamber, that forms what's called a gabbro. Or sometimes this is what's sold at countertop stores as black granite. Okay, there's no such thing as a black granite. That would be a gabbro. They call it maybe a black granite because it shares the property with granite that it's coarsely crystalline. Okay, these materials that freeze in the interior of the earth, they're very well insulated from losing all of their heat. So the crystals that form very slowly, and there's a lot of time for those crystals to gather up their anions and cations and form very large minerals. Okay, so those large, coarse minerals tell us that must have formed in the interior of the earth. There is an intrusive rock or a plutonic rock. Okay, and that's what gabbro and granite share together. They're made of big crystals. Okay, but the mafic materials, the darker, heavier minerals, are called gabbro and basalts. And then if we increase the silica dioxide amount and go to the highest amount of silica dioxide possible, you get the granites, which are made of quartz and feldspar, potassium feldspars and sodium feldspars, maybe small amounts of these more mafic components, again, mostly silica components. Some of the amphiboles and biotites would make up the mafic components. Okay, now if that magma that made up a granite was to extrude on the surface of the earth and form a lava flow, that would freeze as a rhyolite, or a granite that essentially did not have time to form large crystals, so it formed much smaller crystals on the surface of the earth. I have a couple of samples of these. Here's a granite. This is an exceptional granite called the pegmatite that has really large crystals. Here's some of that muscovite, okay, one of the micas that flakes. Here's a much larger crystal called a tourmaline or schorl. And most of the white and grayish color in here are the gray quartz and the whiter colored feldspars. Okay, so this is a granite type material, and that is similar in chemistry to this rhyolite material that comes just not all that far away from my location here in the Oahe Mountains. The pink color comes from the potassium feldspar, and the little white crystals in here are the sodium-rich plagioclase or sodium-rich feldspar, and there are also small crystals of quartz that are here. So same composition as this granite for the most part, same amount of silica dioxide, about 70%, but one formed on the surface of the earth and one cooled intrusively in the interior of the Earth. Okay? As some other examples of these igneous rock, here's what you might call a lava rock, right? If you were over at Home Depot to buy a bag of gravel or a bag of rock, sometimes this is sold as lava rock or scoria, something like this. This is a typical basalt. So this is a mafic material that cooled on the surface of the Earth. Okay, and then slightly more mafic than that, the ultramafic material that's made mostly of olivine. Olivine is a green mineral, so you can see the outer portion of this rock, the weathered portion, is yellow, but the interior is this much more green color, the olivine. This is the peridotite that makes up most of the interior of the Earth. I always like to say the images that I showed earlier in class of the layered Earth, the mantle should be colored green because it's made of olivine. So it should be a green mantle in the textbooks and not a red mantle. But, you know, whatever. I think that really the red illuminates that it's hot in the interior, which is also very true. Okay. So this is really enough that all that I'll say about igneous rocks, and we'll move on to the next rock type, which is sedimentary rocks. So here's a really close picture of a granite showing the quartz crystals, the pink plagioclase, or the orthoclase feldspar crystals, and some of these darker mafics of amphibole.
But it still says igneous.
Yeah, that is still an igneous rock. This is just an example of an igneous rock. Okay, good one. All right, then moving on to sedimentary rocks, the second of the groups of rocks. Sediments are also made of crystals, but these are crystals that have been eroded. These are little bits of rocks that have weathered out or weathered away from the larger rock material, which could be igneous, it could be metamorphic, or it could also be sedimentary. And the processes of weathering and erosion, earth processes, have taken those materials away and washed them away, usually with water. Okay? Water is almost always responsible for these weathering and erosion processes, though wind, aeolian processes could be important as well. So what happens in sedimentary materials is the further away from the source of that main rock, the further away the water takes those little bits of sediments, those little grains, the more well-rounded that material becomes, and the more sort of small or the finer that material becomes as it tumbles down the stream and gets smaller and smaller and smaller and smaller. So when we're looking at sedimentary rocks, those are two of the primary things we look at. How angular are the grains, and how small or large are the grains. So here's the angularity, showing more rounded through time, through being tumbled down the stream. And then here's the different sizes that we use, becoming smaller through time. So these are all really common words that anybody normally uses in their lexicon. But in geology and sedimentology, we have very specific words to describe, or very specific sizes for each one of those words. Boulders, cobbles, pebbles, sand, silts, and muds. Okay? Over here is a picture of what we would call a conglomerate. A conglomerate is the coarsest of the sedimentary rocks. It's made up of real cobble-sized materials. You can have boulder conglomerates as well. Most are pebble to cobble-sized conglomerates. And what's important here is that the sediments are rounded. Okay, here's a nice rounded, looks like some sort of rhyolite pebble. Okay, and here's a nice rounded granite pebble that's been broken in half. Okay, this is a conglomerate that is, it tells us a whole lot of information about the velocity of the water that deposited this sediment. And that's what we try to get to with sedimentary rocks. When we're looking at igneous rocks, we can look at those fundamental features and then make interpretations about whether it cooled in the interior of the Earth or the exterior of the Earth. With sediments, these are always on the exterior of the Earth, but the information that we're trying to understand here is, was this a big, powerful river, or was this a gentle, maybe lake that was depositing things like a shale or really silty or clay-rich material that's forming through suspension settling, where the sediments that are in the lake are just slowly filtering down to the bottom, rather than a river coming by and moving these big boulders and leaving behind, moving some of the sand and leaving behind some of the cobbles that are here. Okay? Another type of sedimentary rock that's very common are the sandstones. Okay, there's a whole variety of sandstones that are out there that we classify based on their composition. And another type of sedimentary rock would be the limestones. Now, this is the first of these rocks that I've shown here or discussed here that is not made of the silica tetrahedra. Okay, so instead, this is made of a mineral called calcite. CaCO3. And this is very similar to what we as humans use that's called cement. So we actually quarry out limestone and we desiccate it or drive off all the water and then use that as a cement and mix that with conglomerate type of material to make concrete. So this stuff, this is just one example of how useful all these earth materials are to us in making buildings and things like this. Okay, calcite is also a dissolvable material. So it slowly dissolves in water, because water is a weak acid. Rainwater contains carbon dioxide from the atmosphere that then makes carbonic acid, which dissolves limestone slowly. So acid rain, which is sulfur-based acid rain, would slowly dissolve the marbles and the limestones of cities where that type of acid rain would fall. Also slowly, just regular water, not any more sulfuric acidic, would slowly dissolve limestones away. Okay, which when calcite breaks apart, it leaves behind the calcium, and the carbonate portion of that effervesces and goes back into the atmosphere. So this is also potentially a carbon dioxide in the atmosphere driver. If you're dissolving more limestones and more marbles, then you're adding more carbon dioxide to the atmosphere. Okay, a little bit more than I intended to go through there. Okay, some of the important sedimentary rocks here that I mentioned: conglomerates, sandstones, and shales. And then here is the calcium carbonate material, or limestone. All right, then the last class of sedimentary rocks, here we are a long ways beyond 50 minutes for this class period, is the metamorphic materials. Now, metamorphic materials, meta is to change and morph to shape. Metamorphic, it's changing its shape. So the fundamental materials here have not changed. It's still generally the same atoms. They've just rearranged and changed shape to sometimes make brand new minerals, or sometimes to just recrystallize together. In either case, oftentimes metamorphic rocks have some sort of fabric to them. Those are called the foliated metamorphic rocks. And here's a really good example of these, of an increasing metamorphic grade. So maybe an increase in temperature in the area or an increase in pressure in the area are going to cause the individual cations and anions of the minerals to rearrange in some way, and maybe during that rearrangement they form a preferential fabric based on the temperature from the region it's coming. Maybe a magma chamber is over here, or from the directed pressure on that area. So we're not going to talk about metamorphic instances in this class specifically, though it's a very interesting topic. So maybe you have a quartz and clay-rich rock like the shale that I was pointing out earlier. Okay, and then if this, if you have a large magma chamber that's over here, adding a lot of heat to this rock, not enough heat to melt it. There's no melting, otherwise, or to form metamorphic rocks. Otherwise, you'd be forming an igneous rock. But if this changed shape enough, where the clay grains grew larger in here and rearranged, it could form what we call a schist. Okay, you can see all these sparklies here are all from the mineral biotite, which is another type of mica, like the muscovite, the sheet muscovite I showed earlier. Okay, so schists and slates are two different types of metamorphic rock that are at different metamorphic grades from one another. Or you might have as intense of a metamorphic rock as a gneiss. These are great names, right? Schist, nice, no schist, be nice. All kinds of great puns you can come up with there on your own. Now, a gneiss is different from a schist because this is actually showing a banding, where some of the more felsic minerals, the higher in silica dioxide, have separated away in bands from the more mafic minerals that have separated away into bands. And these don't really break very easily along those bands either. They're just segregated materials, where oftentimes in the schist and in the slate, because of the micas, these rocks break along their fabric. Okay, that's one easy way to maybe tell these two rocks apart. Okay, and nothing else I really want to say about metamorphic rocks. They oftentimes are the most pretty of the Earth's materials, just fundamentally because of the large micas. They tend to be a lot more sparkly and pretty. Oh, like this one. Look at this beautiful ice. Oh my gosh, it makes my heart melt. Right? I love rocks. Okay, beautiful banded gneiss here with a pocket knife for scale. Thank you, Marley Miller. Okay, so the basic rock names that we just went over that I'd like you to have as a background and knowledge for Violent Earth. Peridotite, that's the ultramafic igneous rock. Basalts and gabbros, mafic igneous rocks. And rhyolites and granites, the felsic igneous rocks. Then, here's their classifications. The sedimentary rocks, conglomerates, bigger rounded materials, sandstones made of sand-sized particles, shales made of silts and clays that oftentimes tend to break apart along those layers of clays. Okay, we call that fissile. And then the limestones made of calcium carbonate, often deposited in the ocean, could be in a lake of certain chemistries. Then the metamorphic rocks, the slates, schists, and gneisses. And one that I didn't show here, but if you take a limestone, a calcium carbonate material, and also induce heat and or pressure, that becomes a marble, okay? A very coarse, coarsely crystalline marble-like material. Okay? So these are the basic rocks that we will use in Violent Earth. Now that we know the Earth's materials, we know that the Earth is a layered Earth, and we have a good background in chemistry, we can move on in the rest of Violent Earth beyond this introductory material and focus on some of these big, catastrophic events that have happened to Earth throughout its history. Okay? The Earth is layered by composition and mechanical properties. Chemistry is really important. Chemistry is the matter that the Earth is made of. Elements of the building blocks of minerals, and minerals are the building blocks of rocks, and rocks are the building block of the Earth. Okay, then rocks can be, the Earth is made of course, these rocks, and they can be classified into these three different types: igneous, sedimentary, and metamorphic, that are created by different Earth processes, normal processes, right? And these processes are not going to be the focus of Violent Earth. We're going to focus on the very rare and catastrophic processes. Okay? So the next material that we'll discuss is our violent origins, or a little bit about the origins of the solar system, and more specifically, the origins of Earth, or the formation of Earth and the Earth-Moon system, okay, which has origins in violence, as these materials, all individual asteroids of Earth or of space, are slamming together to form much larger planetoids and planetesimals. The reading material that you can follow up on based from this last hour and a half worth of information, the Violent Earth Primer, Layers, Chemistry, and Rocks, which is a lot of the same information that just came out of my mouth, but in written format, so you can read some of these words and highlight along the way. Okay, with that, we're finished with Violent Earth Lecture 2. Thanks for hanging in there an hour and a half later. There's a lot of details, a lot of material that I'm putting out there. I'll try to keep these shorter and more succinct to stay on time within 50 or 60 minutes for the class. But I hope you do appreciate some of the extra level of material that I add into this. Okay, with that, thank you very much, and we'll see you next time for Violent Earth Lecture 3, Our Violent Origins.